Hello there, students and friends. Welcome to my high school physics tutorial. In this episode, I'll be discussing problems involving mutual and self-inductance. So stick around, watch and learn. Mutual inductance is where the magnetic flux of two or more coils are linked so that EMF is induced in one coil proportional to the rate of change of current in another. As shown in this diagram, when a changing current I sub 1 in one circuit, for example in coil 1, there is changing current I sub 1. This causes a changing magnetic flux in the second circuit, right? So, in coil number 2, there will be a changing magnetic flux that is produced. And so, an EMF epsilon 2 is induced in the second circuit. All right? And this induced EMF epsilon 2 can be quantitatively determined by using this equation. E sub 2 is equal to negative capital M, which stands for the mutual inductance of the two coils, multiplied by the change in current in coil 1, divided by the change in time, delta T. So, you will notice that the symbol for current is the small letter I, which suggests or implies that the current we are describing is a changing current. It is not the maximum current in the circuit, but a changing current, either increasing or decreasing. Now, likewise, a changing current I sub 2 in the second circuit, all right, will also induce an EMF epsilon 1 in the first circuit. All right, so in the first circuit, there is also an induced EMF epsilon 1, which is just equal to negative capital M delta I sub 2, meaning the current, all right, in coil number 2 over the change in time delta T. So, because of this, there is such term now as mutual inductance. And the capital letter M stands for or denotes this mutual inductance. So, in terms of the magnetic flux and the current, as well as the number of turns in the coil, we say that this mutual inductance, capital M, is just equal to capital N sub 2, meaning the number of turns in coil number 2, multiplied by the magnetic flux, all right, B sub 2. So, the symbol phi sub B2 means this is the changing magnetic flux, all right, in coil number 2, right? Then that is to be divided by the current, the changing current in coil 1. And that is also numerically equal to, right, the number of turns in coil number 1 multiplied by the magnetic flux, or phi base of 1. So phi base of 1 means the change in the magnetic flux in coil number 1 divided by the current, the changing current in coil number 2. In the SI system, the unit of mutual inductance, or simply inductance, is the unit Henry, abbreviated capital H, where 1 Henry is just equal to 1 Weber per ampere, which can also be equated to 1 volt second per ampere or 1 ohm second. And lastly, 1 Henry can also be expressed as 1 joule per ampere squared. If mutual inductance is denoted by capital M, self-inductance, on the other hand, is denoted by capital L. And this is the property of the current carrying coil that resists or opposes the chains of current delta I flowing through it. And as a result of the current I, there is an average magnetic flux denoted by capital Greek letter phi sub b through each turn of the coil. And this self-inductance, capital L, can be determined by just multiplying the number of turns in the coil, okay, multiplied by the changing magnetic flux denoted by the Greek letter, capital Greek letter phi sub b, divided by the changing current, small letter I. Right? So again, we emphasize each of the quantities in this equation. Again, L stands for the self-inductance. Capital N is the number of turns in the coil. Capital Greek letter phi sub b is the flux due to the current through each turn of the coil. Small letter I means the changing current in the coil. So, we say that during self-inductance, which happens if the current, small letter I, in the coil is changing, okay, there is a changing flux through the coil which induces an EMF in the coil. As shown in this diagram, all right, the coil is connected to a battery, and if the current, all right, in the circuit is changing, for example, there is a switch, all right, that you keep on switching on and off, then that's the one way of changing the magnitude of the current I. So, as shown in this diagram, the flow of the charge or the current direction, especially through the coil, is as shown by the arrow. Hence, the change in the magnetic flux, all right, produces a magnetic field denoted here or represented here by the magnetic lines of the magnetic field B. All right. So inside the coil, this direction of the magnetic field lines is from right to left. But the current, as shown, the current in the coil and hence in the entire wire of the circuit is, as shown, it is directed counterclockwise. Right? Now, the equation for determining the induced EMF denoted by Greek letter epsilon, EMF E is just equal to the negative of the self-inductance or simply inductance, capital L, multiplied by the change in the current small I divided by change in time t. Again, we defined each of the quantities in this equation. So epsilon is the self-induced EMF in the circuit. Capital L refers to the inductance of the circuit. And the ratio delta I over delta T means the rate of change of the current in the circuit. So, strictly speaking, the amount of induced EMF depends not really on the amount or magnitude of the current, all right, but it actually depends on how fast, okay, this current changes with time. Hence, the term rate of change of current in the circuit. If the rate of change of the current in the circuit is small, then we expect small amount of the induced EMF. But if delta I over delta T, or the rate of change in the current, is high, that means the current changes rapidly, all right, we will have an induced EMF that is also large. Now, the negative sign is just a reflection of Lenz's law, right? If you recall, in our lesson on electromagnetic induction, Lenz's law states that the change in the magnetic flux, which induces the EMF, okay, it is in fact opposed by the action that causes the change. And to emphasize what Lenz's law is telling us, we put there a negative sign. All right. Our question number 1. A long solenoid with length L, small letter l, and cross-sectional area capital A is closely wound with N1 turns of wire. A coil with N2 turns surrounds it at its center, right? So as shown in our diagram, there are two coils. The first coil has N1 turns, while the second coil has N sub 2 turns, right? The question here is, if you make the solenoid out of twice as much wire, so that it has twice as many turns and is twice as long, how much larger is the mutual inductance presented by or denoted by capital M? Okay. Um, Again, what is described here as the solenoid is the coil with several turns. Okay. If the length of a coil, as represented here by small letter L, is longer than the diameter of the cross-sectional area, all right, it is already called a solenoid. So what is being described in the question, the solenoid refers to coil number 1, the long solenoid with length L and cross-sectional area capital A. All right, so we have 4 options, right? The mutual inductance is option letter A, 4 times greater than the original. Option letter B, twice as great as the original. Option letter C, the mutual inductance is unchanged. And option letter D, the mutual inductance is just 1/4 as great as the original. Right, so we'll have the explanation and of course the answer to this question in just a short while. To answer this question, okay, we refer to the formula or equation for mutual inductance capital M being equal to N2 uh, P sub B2 divided by small letter I1. That is also equal to N1 P sub B1 over I sub 2. Right. Our explanation: if we double the length of the solenoid L and the number of turns of wire in the solenoid N1, the mutual inductance capital M would remain unchanged. So it's not going to double, or it's not going to increase 4 times, but it will remain the same as the original. This is because the magnetic field capital B produced by the solenoid, okay, depends only on, aside from the current, it depends on the number of turns capital M per unit length, and not just on the length of the solenoid alone, or on the number of turns, okay, of the coil in the solenoid alone. Because based on our previous concept discussed on electromagnetic magnetism, all right, we said that the magnetic field B for a coil that is long, we call it a solenoid, the formula is just multiplying the what we call permeability constant and the number of turns per unit length, small letter n, and of course to be multiplied by the current. All right. So when you say small n, it actually refers to the big N divided by the length of the solenoid. So it is the number of turns per unit length, okay, that directly affects the magnetic field, all right, and not the length of the solenoid alone, neither the number of turns of the coil alone. So if this factor affects the magnetic field B, it follows that the magnetic flux, okay, a Greek letter capital P, will also be affected by this number of turns per unit length. In short, the mutual uh, inductance capital M will also be affected by the number of turns per unit length. Moving on now to question number 2. The mutual inductance of two coils, coil 1 and coil 2, is 48.0 microhenry. Find the magnitude of the EMF induced in coil 2 if the current in coil 1 is letter A, 35.0 amperes and increasing at 7.00 amperes per second. Letter B, 28.0 amperes and constant. Letter C, 26.0 amperes and decreasing at 3.00 amperes per second. Alright, so in our diagram, we have the two coils. The one with the, what we call, with the larger number of turns is coil 1. Alright, and the one outside with fewer number of turns is coil 2. And what is asked in the question is to determine the magnitude, or just the value of the EMF induced in coil 2. So our solution requires us to use the formula for finding the EMF induced in coil 2, and that is equal to epsilon 2 equals negative capital M, the mutual inductance, uh, multiplied by the change in the current in coil 1 divided by delta T, or the change in time. Take note, delta I sub 1 divided by delta T is called the rate of increase. For letter A, the rate of increase in the current, right? So substituting, we have epsilon 2 equals um, the value for the mutual inductance, 48.0 times 10 to the negative 6 Henry, and multiplied by the rate of increase in the current, 7.00 ampere per second. There is no need to indicate the minus sign because the question is only referring to the magnitude of the EMF. All right? And simplifying, we will get the value for epsilon 2, or the induced EMF in coil 2, equal to 3.36 times 10 to the negative 4 volts. All right? How we arrive at this final unit, well, I leave that to you to show to yourself how multiplying Henry by the unit ampere and then per second we will arrive at the unit volt. We are sure that the unit for the EMF is volt because Henry is the SI unit for mutual inductance, ampere is the SI unit for current, and of course second is the SI unit for time. All right. Question letter B. All right. What is the induced EMF if a current of 28.0 amperes, all right, is in coil number 1, but it is constant? The answer is there is no induced EMF in coil 2. Epsilon 2 is equal to 0. The reason is that only a changing current in the first coil can induce an EMF in the second coil. Right? Since 28.0 amperes in the first coil is a steady current, it is neither increasing nor decreasing. Hence, there will be no what we call induced EMF in coil 2. But in letter C, all right, we are given the amount of current initially at 26.0 ampere, but is decreasing at a rate of 3.00 ampere per second. So there will be an induced EMF epsilon 2, all right, which is just the product of the given mutual inductance capital M, again disregarding the sign, negative sign, 48.0 raised to the negative 6 Henry, and multiplied by the rate of decrease in the current, which is 3.00 ampere per second, and we will get the value for EMF in the second coil, or epsilon 2, equal to 1.44 times 10 to the negative 4 volts. Moving on to question number 3. A long straight solenoid has 800 turns. When the current in the solenoid is 2.90 amperes, the average flux through each turn of the solenoid is 3.25 times 10 to the negative 3 Weber. Question: what must be the magnitude of the rate of change of the current in order for self-induced EMF to equal 6.20 millivolts? Alright, so in answering this question, we first calculate for the self-inductance, capital L, using this formula. Okay, capital L is equal to the number of turns in the coil multiplied by the average magnetic flux, denoted here by the Greek letter P sub B, and divided by the current I. And then after getting the self-inductance, capital L, we can already use the formula for the rate of change in the current, delta I over delta T, simply by dividing the self-induced EMF, or epsilon, divided by the uh, self-inductance, capital L. Alright, so using the formula for self-inductance, capital L, which is equal to capital N, Greek letter phi, so B, which represents the average magnetic flux induced in the coil, with to be divided by the amount of uh, the changing current I. Substituting 800 turns multiplied by the amount of average magnetic flux, 3.25 times 10 to the negative 3 Weber, and divided by 2.90 amperes. Doing our math, we will get the value for self-inductance, capital L, equal to 0.897 Henry. All right? So using the formula for the rate of change in the current, delta I over delta T, which is just equal to the amount of self-induced EMF divided by the amount of self-inductance, capital L, and substituting the given EMF, 6.20 millivolts, or in volts, that's 6.20 times 10 to the negative 3 volts, and divided by the amount of self-inductance, 0.897. Instead of Henry, we change it to Weber per ampere, right? And simplifying, we will get the rate of change in the current being equal to 6.91 times 10 to the negative 3 amperes per second. So that is the rate of change in the current that induces the amount of uh, EMF given here, and the self-inductance that's also given here, 0.897 Henry. Note that how we were able to come up with the unit of the rate of change in the current as ampere per second, because Weber can also be expressed as 1 volt second, right? So if you substitute, instead of Weber, we have 1 volt, or 0.897 volt second. Eventually, the unit volt cancels out, and we are left with ampere per second as the final unit of our answer. We're down to our last question. Number 4. A solenoid 25.0 centimeters long and with a cross-sectional area of 0.500 centimeters squared contains 400 turns of wire and carries a current of 80.0 amperes. Calculate the following. Letter A, the magnetic field in the solenoid. Letter B, the energy density in the magnetic field if the solenoid is filled with air. Letter C, the inductance of the solenoid. And letter D, the total energy contained in the coil's magnetic field, assuming that the field is uniform. To calculate for the magnetic field in the solenoid, we use the formula B equals a constant known as permeability of free space, mu naught, times the current, I, and the number of turns per unit length, or N, over L. Substituting 4 pi times 10 to the negative 7 Weber per ampere meter times 80.0 ampere and times 400 per 0.25 meters. Simplifying, we will get the value for the magnetic field in the solenoid equal to 1.61 times 10 to the negative 1 Tesla. For letter B, okay, we are asked to find the energy density in the magnetic field if the solenoid is filled with air. Okay, we denote that by small letter u. The formula is energy density U is equal to the square of the magnetic field B divided by twice the what we call relative permeability of the material, in this case air, where mu, or the relative permeability of air, is just equal to a constant K, and for the material air, the value for K is just equal to 1. It is a unitless constant. And then multiplied by the permeability of free space, mu sub naught, which is 4 pi times 10 to the negative 7 Weber per ampere meter. Alright, so let's substitute. The square of the magnetic field computed in letter A, 1.61 times 10 to negative 1 Tesla. That will be squared, to be divided by twice the relative permeability of air, or 2 times 4 pi raised to the negative 7 Tesla meter per ampere. Alright, instead of using Weber per ampere meter, we use Tesla meter per ampere. That's the value for twice the relative permeability of air. Doing our math, we will get as the value for the energy density, alright, equal to 1.03 times 10 to the 4th power joules per meter cube. And for letter C, we are looking for the self-inductance, capital L. Okay, the self-inductance in the solenoid, which is just equal to the number of turns in the coil multiplied by the average magnetic flux, Greek capital letter B, divided by the amount of the current, small letter I. Substituting 400 turns to be multiplied by the amount of the magnetic field computed in letter A, 1.61 times 10 to the negative 1 Tesla. Alright? That magnetic field, when multiplied to the cross-sectional area, which is 5.00 times 10 to the negative 5 meters squared, okay, this gives us the average magnetic flux, or Greek capital letter B, still to be divided by the amount of current, 80.0 amperes. And we will get the value for the self-inductance, capital L, equal to 4.03 times 10 to the negative 6 Henry. And finally, answer to our question letter D, we are looking for the total energy that is contained in the coil's magnetic field, and that is denoted by capital letter U. That is equal to 1/2 the product of the self-inductance, capital L, and the square of the current, I squared. Substituting, we get 1/2 times 4.03 times 10 to the negative 6 Henry to be multiplied by the square of the current, 80.0 amperes. And simplifying, we will get as the value for the total energy contained in the coil's magnetic field, capital U, which is 1.29 times 10 to the negative 2 joules. Alright, so we are done with our uh, video tutorial. Thank you very much. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.